Alright guys, so this video is going to be about electric force and electric potential. So we've talked about charge and conductors and insulators and different ways to charge an object. But now we're going to look a little bit more in depth at this idea of charge and the fact that when more than one charge exists in a region of space, they're going to feel a force due to each other. And also that system will have some potential energy. So we're going to learn how to calculate that as well. So when we look at electric force, the equation we use is very similar to Newton's law of gravitation. And the equation is Coulomb's law. And so, actually, before I show you the equation, let's try this. So what we're doing is we're talking about a situation where we have two charges. So I'm going to call this Q1. I'm going to call this, put that down there, Q2 over here. Okay, so I have two charges, and there'll be a certain distance between them. And as we talked about, if they're the same sign, if they're both positive or both negative, they're going to repel each other. And if they have opposite signs, then they'll attract each other. But no matter what, we can get the magnitude of it using this equation. We can get the magnitude of this force using this equation. So we have the electric force, so force electric, is equal to some constant K. So this K is called Coulomb's constant. And it has a value of 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Okay, so we're going to be using coulombs here. Now notice how big this value is. This constant that we use in this equation is a lot bigger than the 6.67 times 10 to the minus 11th that we used in Newton's law of gravitation for big G. And that's because the electric force is a lot stronger than the gravitational forces. We need a lot of mass, like planets and suns, in order to produce a gravitational field capable of exerting a large force, whereas with charge, we don't need much charge at all in order to have it produce a field that produces a force that we would notice. So K is the first part of this equation. And then we take the product of the two charges. Okay, so these are the charges. And this is in coulombs. Now you gotta be careful here because a coulomb's a lot of charge. And so we don't often give charges in terms of coulombs. We give charges in terms of microcoulombs or millicoulombs. So if you need to learn your metric prefixes again, please do so because you're going to be seeing a lot in these problems because you're going to be given in millicoulombs, microcoulombs, maybe even nanocoulombs, and you have to translate them into just coulombs without the prefix. And then we say divide by r squared. This is the distance between the charges. The distance between charges. And this is going to be in meters. Okay, so we always use meters here. So this is Coulomb's law right here, okay, this equation. And as you see, it's very similar to Newton's law of gravitation. Newton's law of gravitation, just real quick to kind of, right, it said big G, M1, M2 over R squared. So it's got really the same form. It's got a different constant. We're using charge instead of mass. Okay, but what it looks like is the same. This is an inverse square law. Okay, so this is an inverse square law. So it's got the form, it's proportional to 1 over r squared. So once again, if we, say, double the distance between the charges, the force will go down by 4. If we cut the distance and make it 1/3 what it was before, then the force will increase by 9. Okay, so it's always 1 over the distance between them squared. Okay, so how do we use this? Okay, how do we use this? And so I'm going to ask you guys to kind of quickly solve a problem using Coulomb's law. And so say we had a 30 microcoulomb charge and it's placed 20 centimeters away from a charge that's negative 20 microcoulombs. And then what's the magnitude of the force between them? Okay, so use Coulomb's law that you just wrote down your notes to solve for that. And make sure you can do that successfully. And then kind of a follow-up question, just notice there's 2 A's here, this should be B. Kind of a follow-up question: why does the force have a negative sign? So when you plug the numbers in and you have like a negative, 20 and 30 and all that, you're going to get a negative force. And so what's the meaning of the negative sign? I want you guys to think about that. So answer these two questions in your notes quickly and pause the video as you do this. And then when you're ready, you can unpause the video and see the answers. Okay, so when we look at the magnitude of the force between them, the magnitude of the force is going to be 135 newtons. And that is shown right here. So this is Coulomb's law. This is our K. Notice that we have to use 10 to the minus 6 because that's what this micro means right here. 10 to the minus 6. So 30 times 10 to the minus 6 coulombs times negative 20 times 10 to the minus 6 coulombs. Divided by, we have to use meters instead of centimeters. So it's going to be 0.2 meters squared. Okay, and we get negative 135 coulombs. So the question is, okay, well, what's the negative mean? The negative sign indicates that the force between them is attractive. So students are always, kind of confused by this when they use Coulomb's law. They get a negative force, and like, what does that mean? All a negative force means when you use Coulomb's law is that the two charges are attracting each other. If you get a positive force, that means that both the charges would be positive or both the charges would be negative. They're like charges and they repel each other. Okay, so that's all the negative sign means. So the sign of the force does carry information in Coulomb's law. It tells you whether the force is attractive or repulsive between the two charges. Okay, so if we have a force, it's kind of the same progression we used when we talked about, masses and, and mechanics. We had a force and we started talking about energy and how we can look at things in terms of energy. And so we consider a case where we have, instead of having like say mass here, maybe we have a charge here. I'm going to make this plus, we can make a capital Q so we can more easily distinguish it. And you can imagine that we have another charge out here, and I'm going to call this lowercase q. Okay, and we're going to make this we're going to make both of these positive. One of the issues we have with electricity is that the electric force can be, as we just talked about, it can be attractive or can be repulsive. Now that's different than gravity. Gravity is always going to be attractive. And so what we have to do is we have to define everything, like as far as like energy and forces and the direction of forces, and later on the course fields, we have to define everything in terms of either what a positive charge would feel or what a negative charge would feel. And we choose a positive charge in physics. It was just a historical convention. So we're going to look at positive charges here. And you imagine that if I was at infinity, okay, there would be no force between these two, okay, because I'd be an infinite distance away, and like 1 over infinity squared would, it should be 0, right? But then you imagine I take this charge and I start to bring it in. And as I did that, I would have to do work in order to do this. I would have to do work in order to do this. And so the work that I would do on that charge to bring it to a certain point right here, and say that this point is some distance r away from the other charge. Okay, the amount of work I would have to do would be equal, it would be building up potential energy. Okay, it's hard for us to imagine a charge. It might be easier to imagine magnets. You take two like poles of a magnet, and you bring them together. You have to exert a force, and you have to move at a distance. You're doing work, and the amount of work that you exert is equal to the potential energy that you build up in that system. Now, to really derive this, you have to use calculus. If we use a point charge, you have to use calculus. We're not going to worry about that, but so unfortunately, maybe you just have to trust me on this. The electric potential energy for the system, so when we talk about potential energy, it's always a system of two charges. The electric potential energy would be K big Q times little q divided by the distance between them. Okay, so this is the equation for electric potential energy of two charges. So you have the two charges. You have K, which is again Coulomb's constant. R is the distance between them. Okay, and yes, that does mean if you have opposite charges, there's a negative potential energy. So like I said, we defined everything in terms of what a positive charge would experience or have. So this equation is for the electric potential energy of a system. So if I were to bring this here to some distance r, I could use this, I would calculate this, and that's how many joules of potential energy I would have stored up in the system. And then if I were to let the charge go and it would fly off, this would have, imagine kind of like putting a pin in this charge here, this charge would fly off and the kinetic energy it would have would be equal to the potential energy that it started with. Okay, so that's the equation for electric potential energy. And then finally, one thing we do with electricity is rather than just talk about electric potential energy, there's something called electric potential. Now this can be it can be a little confusing, and the reason why is because we don't really talk about a gravitational potential, right? So this is something that, at least when you first learn it, it's pretty unique to electricity. So let me explain before I get into the nitty-gritty here why we're doing this. So say that's, once again, we have our charge Q here. Okay, rather than calculating a potential energy for every time we have a new charge, what we do is we can say, okay, we have this spot in space. Okay, even if a charge doesn't exist there, we have a spot in space, and we kind of say, you know what, is there some number I could use so that if I did put a charge here, I can multiply that charge by the number for this point in space, and that would give me the potential energy of the charge that I put here. Okay, now we have this charge around because without it, there would be no potential energy. So we need this charge right here. And so this number that we use is called the electric potential. Okay, so for right now, you can see the electric potential as being the number that I would multiply by a charge that I put here that would give me the potential energy of the charge that I put there. Okay, so let's say I'm going to put, I'm going to place a charge right there now. I'm going to look at this potential energy equation again. I'm going to rewrite it a little bit differently. I'm going to say it's K Q divided by R times Q. So this is the charge that we're placing at that point in space. But this quantity right here, this K times the big Q over here divided by R, which is the distance out to this point in space, it doesn't matter what this is. This number, which is the electric potential, is what I could multiply by any charge I put there and get the potential energy for my system. Okay. So that's what electric potential is. It's a property of a point in space. There doesn't have to be a charge where the x is. Okay, we can still say that there's a certain electric potential there. But then as soon as we do put a charge there, we can calculate its potential energy by multiplying it by our electric potential. Now, that's all kind of, it's kind of abstract. But the reason why we're talking about it is because this applies to circuits. And so what I want you guys to remember is that a positive charge moves from high to low potential. So you can imagine that, we have the x here, and maybe we have another point out here. So these are 2 points in space. This point would have a high potential, and this point would have a lower potential. And if Q is a positive charge, so I'm talking about this Q, this little q right here, if that's a positive charge, it's naturally going to move from a high to a low potential. Okay, so positive charge will move from a high to low potential. Negative charge does the opposite, by the way. So a negative charge will go from a lower potential to a higher potential. So a negative charge would spontaneously move this way. Okay, but as I said, our convention is kind of to use a positive charge, and so we're going to think about this. And this moving of a charge, the spontaneous movement of a charge from a high to a low potential, is why current runs in a circuit. And that's why we're talking about this, because when we get to circuits, we're going to notice that there's going to be a current going through the circuit. And the reason why is because one terminal of the battery is at a high potential, the other terminal is at a low potential, and so we imagine positive charge spontaneously moving from the high potential terminal of the battery to the low potential terminal of the battery. Okay, So I hope all that makes sense. If you guys have any questions, please let me know. We will certainly talk about this more in class.